So welcome everyone to the last day of SGP 2024. Today I'm delighted to introduce Josephine Carstensen. Josephine is assistant professor in MIT's Department of Civil and Environment Engineering. She received awards for both research and education, including the NSF Career Award and the CEE Massey Award for Excellence in Teaching. Her research focuses on computational design and topology optimization, and this is a field that faces many geometry-related challenges, as we will learn today. So please welcome Josephine.
Thank you so much for the introduction, and thank you for having me here. I'm really excited to get to share with you today some of the recent work that we've been doing, especially emphasizing our work on human-guided geometry processing in high-performance engineering design. I did it already once, and I am sure I will do it again over the next hour or so. I said we, and so I thought it'd be polite to start off by introducing you to who I mean when I say we. I mean myself, our collaborators, but perhaps most importantly, the 10 talented students that I have the pleasure of working with here at MIT. The thing that we are collectively working on is aiding the identification of high-performance engineering designs. We're using primarily a technology called topology optimization, and we're doing that because it actually allows us to forget about the geometry for a second and start off by focusing on how we want our design to function. So if a designer can define a bounding box, relevant operating conditions for how the design is going to perform when it's out there in the real world, that could be how it's going to be supported, what loads it's going to meet, or is it going to meet thermal fluctuations and whatnot. We can give this information to the topology optimization algorithm that then essentially helps us figure out, okay, where do we place material? And this has been known to lead to new and often surprising solutions that tend to outperform conventional low-weight design quite significantly. So in this example here, we can get a 42% stiffer beam with the same weight. And if we were to ask the question differently, how low can we go? We can get an almost 50% lighter beam with the same elastic stiffness. Now this sounds amazing, sounds great, but I'm not trying to sell anybody a free breakfast here. You already had that outside. These approaches is by no means necessarily easy to set up and solve a design problem. And we're also left with these really great-looking computational structures, but perhaps a bit of a head-scratching question of how do we take it out of the computer and into the real world? How do we actually fabricate or construct them? And that's really important to us because we are on the engineering side of the community, and we are really interested in the end goal being the physical structure. I'm going to come back lots to these two problem areas. But before I do that, I'd like to give you a little bit of a feel for what solving a design problem like this looks like. So what we're going to be doing together is we're going to be designing this cantilever beam that's fixed at one end. So imagine that it's held in place where there are little lines. And then at the end of the middle of the tip, there's a load applied. So something is pulling it down. The first thing we'll do is we'll formulate the design task as a formal mathematical optimization problem, meaning we'll define an objective. In this case, it's going to be minimizing the compliance. That's equivalent to asking for a very stiff structure, so something that doesn't really deflect a lot when we pull on it. It has to make physical sense. The load has to be transferred from the point of application to the boundary conditions. And to make sure that that happens, we're going to be enforcing a static equilibrium. And that means that we're going to be solving a finite element problem within each design iteration. You can probably already hear that we're going to be using computational resources to do this. We can apply a mass or a volume constraint telling the algorithm how much material it's allowed to use. And finally, we need to define some design variable bounds to make the problem solvable. You'll notice that these bounds are defined as continuous and not as strict 0, 1, which is really what ideally we're looking for. But in most of what I'll show today, we're doing what pretty much everybody else does. We are allowing the existence of fictitious intermediate material and then penalizing it using standard penalization methods. Mainly, we're using SIMP. A little bit more of the fine print. We're using the method of removing asymptotes for almost everything we're solving, calculating sensitivities of the problem using the adjoint method. And you need a filter, because otherwise you're going to run into numerical instabilities, mainly related to the finite element calculation. And so for most of what we're doing, we're using the Heaviside projection method as the filtering method. And so let's solve the problem. Gray is going to be, I don't know, fictitious. Maybe I want to be void. Maybe I want to be solid. Black is going to be solid material, and void is going to be indicated in white. Now, in setting up this design problem, I made one more engineering decision. I decided that our design here would be well represented by a 2D space, and I therefore discretized the design space using 2D continuum elements. We could have picked something else. We could have said what we're planning to make is really more like a truss structure, so I'll use discrete line elements, either in 2D or in 3D. We could have said what we're planning to make is really something that's a three-dimensional structure in its nature. I'll find a 3D volume, discretize it with 3D continuum elements. The method is largely the same. There's a little bit of a jump from the truss to the continuum, but the approach sort of stays constant. And so to come back to the question of why are we doing this? I already said that it's not necessarily easy to set up and solve. We have problems making it. So why on earth am I spending a good chunk of my career developing these design approaches, or even more importantly, why am I convincing 10 students to spend their valuable time researching this? And the reason that we keep coming back to is that the way we're thinking about manufacturing is changing. The way we thought about making things 10, 20 years ago is pretty dramatically different from how we're thinking about making today. When I started undergrad, that's just about 20 years ago, next year, there was no such thing as 3D printing. I remember when the first MakerBot type printer arrived on the campus I was at back in Denmark, and students were not allowed anywhere near that thing. We were not even allowed in the room, right? Fast forward to today, I have an 8-year-old daughter that goes to public school here in Massachusetts. And she has access every day during the school year to a 3D printer at her school. Should it, for one reason or another, be down, that does happen, she can cross the street to the public library and check one out and bring it home. And what I'd like you to do is just fast forward that process another 20 years and just think where we might be. To illustrate what I'm talking about, what's playing here behind me is the opening credit to the HBO series Westworld, where robotic spatial extrusion is being used to print humanoid robots. There's research ongoing, but I believe the humanoid robot part is still under development. Robotic spatial extrusion certainly is not science fiction anymore. It's being used in research labs and startups across the world to build structures that are up to pavilion scale, so things you can walk into. And it's exciting because it means we can make new complex things, but we can't make anything. With robotic spatial extrusion, you can print diagonally, but only for so long before you start sagging. You can go in and add members to a node, but you can't do it an infinite amount of times because then the robot will destroy what it's already placed. So what we're really interested in is developing these new design frameworks that help us explore what is possible within this new manufacturing paradigm. And in doing so, we need to have a conversation about what that means for the designer. I think for the past couple of decades, research in topology optimization has really been focused on taking the designer out of the equation. So the designer defines the design problem, the algorithm returns a design, in this case it's a mechanism design, and then this design fits whatever way you're thinking about making it, and it goes like directly, it's fully integrated. Reality is not quite like this yet, maybe it never will be, because we do have this human with preferences that enters the equation somehow. At current, it's maybe a little bit like the algorithm returns the design, it goes to the human. On a good day, the human is like, yes, go ahead, print it. But perhaps more frequently, the human looks at the design and is like, yeah, I'm not fully satisfied. In this case here, the human might look at this one-node hinge and be like, this looks great on the screen, but if I print it, who knows if it will stick together, and if I start putting load on it, it will certainly break. I'm not happy with this at all. And so the human will go back and change something. That something can be the hyperparameters of the algorithm, it can be the settings of the design. By that I mean the minimum feature sizes, how much volume you're allowed to use, or maybe even the design problem formulation. For this particular case, the human might adopt what's called a robust formulation that's known to get rid of these hinges, and if we're lucky, that's enough to say, yes, please go ahead. And so one of the interests that we have in our group at the moment is really how do we short circuit this outer iteration loop that's super hard to quantify how much time you might spend on, and make it easier for the human to get something that they're like, yeah, I'm happy with that. Let's go ahead and fabricate. Because if we get there, if we manage to get something that the human accepts, then the combination of advanced manufacturing and these new computational ideas really allows us to realize improved designs. I'll give you a quick example of what I mean by that. So humans have been building with timber for pretty much as long as we've been building anything. And when we've been doing so, one popular way of putting timber member 1, timber member 2, timber member 3 together is through interlocking joints, where we put them together, they have a geometric pattern. It means that they block movement from each other. The oldest known example dates back to 5,000 years before the current era, and is found on the bottom of a weld in Poland. We can find different examples of these interlocking geometries in timber throughout different civilizations across the world, and they will be associated with different levels of geometric complexity. But when you look at these, what you'll notice pretty quickly is that they're all governed by these straight lines. And these stem from the different woodworking traditions' abilities with saws and chisels. I'm horrible with a saw, even worse with a chisel, but we don't have this restriction anymore because we have access to digital fabrication, digital carving, CNC machining, and so we really have the opportunity to go in and explore this space, look at what are the shapes that come together, can be assembled, disassembled, possibly if we want them to, and in this case, improve the stiffness of the joint by about 30%. And it's not just exciting because we can make these new things. It's also exciting because there are some areas where we really need to rethink how we approach design. And one such area is my home domain of civil engineering. And I say that not just because I'm a passionate structural engineer, I say that based on data like the one showed in the chart here from the UN Environmental Status Report. This chart is mapping out the global annual carbon emissions by sector. And we see the big bad guys that we talk about a lot, right? We talk a lot about how industry in general is a massive carbon emitter, how transportation is a huge source of carbon emissions. What we've perhaps spent less time worrying about is the fact that building and construction materials alone account for 11% of the global annual emissions. And in this context, the global cement production, which is, you can think of as the glue that you need to put concrete together, is by far the biggest contributor. I won't think any ill of you if you look at this and say, 11%, what she's talking about, we've got bigger fish to fry. But this is not a problem that's likely to go away by itself. When we look at what is predicted to happen in terms of global population growth, we're going to be 10 billion people on Earth. That's 2 more than today by the end of the century. And these people are primarily going to be located in urban areas. It also comes down to the fact that we're going to need to build a significant amount more than what we're doing today. And so all predictions for what that means is that we're going to need to use a lot more construction material. The top bar here, sand, gravel, and crushed rocks, that's essentially the recipe for concrete, okay? So the consumption that we have today is predicted to double by 2060. If we're really going to need to build more, we should start at least thinking about doing it in a more carbon-friendly way. And the first step in getting there would be to at least quantify how much carbon do we think is going to go into a structure that we're putting up. That can be done using a formula like this for the global warming potential. It's a pretty simple formula. Sum up over everything that you have in your structure, so your columns, your beams, your roofing material, the floor. Take the weight of each element and multiply it by a materially specific embodied carbon coefficient. Now this coefficient also depends on where you are in the world, so it's a great idea to use bamboo in Asia, maybe a little bit less great in California. What this formula indicates is that we really have 2 major knobs to turn. The first one being the embodied carbon coefficient of the material. And at current, this is the most popular approach to trying to reduce the carbon of new construction. The idea is we use something with a smaller embodied carbon coefficient, we get a more carbon-friendly design. And so the overarching theme is let's design structures that use alternative materials. In this context, timber is a very popular material to use. Now, when we use alternative materials, they will not have the same mechanical properties as conventional construction materials, concrete, steel. And so it might not be beneficial from a carbon perspective to just switch out everything with timber. It might be beneficial to do something like a hybrid design. And so to facilitate discovery of that type of solutions, we created a couple of years ago this truss topology optimization algorithm that simultaneously designs the size of the member and determines if it should be made of timber or steel. And in this context, we could show that we could achieve an additional 10% carbon reductions over structures that were already optimized, where you go in and manually select the material. Our work in this direction is at the moment focusing on incorporating realistic fabrication or construction constraints such that you can limit the amount of members that goes into a single node that has a direct influence on the price of making the connection. And also specifying a clearance angle between members coming into a node. Now that's not just important for the price of making the connection, it's also important for inspection later on as the structure is functioning. We could come back to this formula and we could say, small is not really good enough. Could we ideally go to 0? That's probably not going to be possible as long as we are building. But one way that we can get really close is by reusing more of things that we are right now discarding as trash, as Keith was talking about in his poster presentation the other day. I took this picture about a year and a half ago, about 30 miles west of here, near a strip mall close to where I live, where a physical bookstore was being taken down to make room for a warehouse for an online bookstore. Unfortunately, I'd forgotten my phone the week before, where they had just taken down all the roof trusses from the previous building. They were laying super nicely in big piles, almost perfect, a little bit crinkled at the end, ready to be taken off, remelted, and made into new recycled steel products. 6 months after that, new trucks came in, near identical trusses, a little bit shorter because the span of the new building is shorter, to make up the new room of the roof of the new structure. Now, this is, of course, just one simplistic example, but there are really millions of these, so it's well documented that the potential for reuse in construction is significant. It's associated with a bunch of challenges, and some of these have to do with the geometry and the design. One is that when we're designing trusses today, we're really thinking, okay, we pick from a catalog of what capacities or what sections we have available, and for each of these we can get like an infinite length almost, whatever fits on a truck. That's pretty different from if we take something down and we are restricted to whatever library that is available within the existing structure. So here, using graphic statics as the driver, we've created an algorithm where we generate efficient truss shapes, and we do it in a way where we can create many. And having many options to choose from is actually pretty important for reclaimed construction, because from the time that you plan to take down a building to the day that you're putting up the new building, your library might have changed slightly. Something might be ruined when you take it down. Another problem that's associated with reuse is that the demolition or deconstruction process is all of a sudden much bigger, right? If we're just taking something out to throw it out, we're not going to be as careful. And also, if we're taking something out and have to dismantle it completely into sticks before we can start thinking about designing with it again, that is going to be costly. And so we've been toying with this idea of only requiring partial disassembly, for instance, to triangular components, and then making it easy to aggregate these components into new shapes, doing it so fast that we can wrap an optimizer around it to help us identify high-performing solutions for our new structures. Coming back to the global warming potential formula, we could, of course, also address the elephant in the room and say, how about using less material? That is what I will talk about for the rest of the talk today. In this context, of course, it makes most sense to talk about how we reduce concrete construction through efficient design. We've done some preliminary work on this where we've used topology optimization to simultaneously design the layout of the concrete face and reinforcement face that you need, so the steel you need inside concrete, and shown that we can take out at least 25% of the problematic concrete face and still maintain the exact same elastic performance as what we accept as the standard today. If we are to be successful in doing this, we need to be sure that the algorithms that we're using incorporate all relevant behavioral characteristics. So for the case of reinforced concrete, the fact that concrete has a different material behavior than steel, and also the fabrication characteristics. So, and we want to do that so that the results that we present to the designer is something that is credible, behaves as predicted, and is easy to fabricate. One more thing, though, as if that first bit wasn't hard enough, is that we need to make sure that the frameworks that we are proposing fits the industry-specific needs. And those needs are pretty different for a design engineer who sits at NASA and works for months on a little thing that gets sent into space than for a structural engineer who designs 100 highway bridges in a year. And so to roll out what that might look like, we conducted a survey last year of structural engineering practice in the northeastern US. And as part of the survey, we presented our participants with 3 different case studies, one on parametric design, one on shape optimization, and one on topology optimization. And after reading about these case studies, we asked our participants, in a future project on a scale from never in a million years to, yeah, I drank the Kool-Aid, would you be willing to use this type of design tool? Not surprisingly, the more simplistic design tool of parametric design tended to have a response of yes. For shape and topology optimization, we were surprised to see that it was about 50-50 of who would be able to or willing to use it or not. And perhaps even more surprisingly, the complexity of the 2 designs didn't seem to influence the response rate at all. Participants were just as likely to say yes to shape optimization as they were to topology optimization. More importantly, we asked our participants to tell us what barriers they face in adopting automated tools in their design practice. We had suspected that constructability would be a big issue, and it was reported frequently, but it was not actually the most popular response. Most of our participants had concerns about what it means for the design time. That is the time it takes to run a tool, the lack of training or the learning curve associated with adopting a new tools. Some concerns about the tools themselves, that they don't have access to it, that they feel they get better results if they design by hand, and that the tools are too black box in nature. And a category that we've dubbed other that includes considerations that are pretty important, such as the perception that using an automated design tools will limit the future use. And that's important if you're building something for 50 to 100 years. There is also the perception that there's not enough gain associated with it. You invest all this time, and the end product that you get is not even worth it. We asked about the different tools of the case studies, and specifically for topology optimization, we can see even more clearly constructability as a concern, but not the biggest one. The biggest concern pertains to the time increase or the cost increase associated with it. And so we've spent a number of hours trying to figure out, okay, where does time go then? Where can we win some time? And we've deciphered the time associated with topology optimization into these 3 major categories. One being the time that it takes to set up your problem. So identify what is realistic for my particular operating situation. How do I formulate the problem? How do I derive sensitivities? How do I implement it? Then there's the time associated with actually running the algorithm, which of course depends on your computational resources, where many of these civil engineering practices and others, they don't have a lot of computational resources available. And then finally, there is this obscure, super expertise-dependent time that goes into setting the hyperparameters of the problem so that you get this solution that you're likely to accept. We're working on addressing all 3 of these issues, but what I'll show today is the thoughts we have on how we might be able to speed up the setup and runtime. And just to get back to the overall goal of this, we're really interested in giving the human, presenting the human with something they're likely to say yes to. So how do we do that? And the goal that we have is to keep having the computer doing what it's good at. We would like to maintain the computational explorational power that's associated with topology optimization, but we're thinking that maybe if we make the user an active in the process to nudge towards a direction they're likely to accept, we might be able to solve less complex problems and still inject some of the experience from the design engineer. Initially, we did this by playing with the minimum feature sizes of the design, and we did that because we think that that's a good proxy for mechanical behavior. I'm showing here a column in buckling, so it's a column that's being compressed directly, actually, and what's happening is a mechanical instability that's making the mid of the column go in the opposite direction, kind of like if you ever try to press on a ruler. Now, if you have experience in engineering mechanics, you'll probably look at this and say, okay, if you want me to improve the buckling load and say I can't change the material, I'll just make this thicker. And then this is less likely to happen, or it will happen at a higher load. And so that's the type of idea that we've been implementing. So here we're showing regular compliance-based topology optimization, and after about 50 iterations, we're interrupting it. And here the design is formed. We present the user with a stress plot and ask them if they're happy. In this particular case, there's a stress concentration at the entrant corner, and in response, the human user is saying, I know how I can make that better. I can put a bigger fillet radius in this particular corner. The algorithm then proceeds with this fillet radius going forward, and we see it's trying to do something to alleviate it. And again, after 50 iterations, we're interrupting, asking the user essentially, are you happy now? We can see that the stress concentration has been reduced. For one reason or another, the human is still not satisfied, find this particular member down here too stocky, and applies a maximum length scale locally within this region that then proceeds to split up the member. Now, this video is chopped a bit and sped up for the sake of this presentation. From setting up the design problem in a rudimentary GUI we've created to full convergence of this problem takes about 5.5 minutes. So still quite a lot faster than, say, running with stress constraints. Coming back to the issue of buckling, the classic topology optimization benchmark problem for buckling is this short cantilever beam, where the compliance design will give you a 2-bar structure. Now, we're imagining that the experienced engineer will go in and say, the bottom member is where compression will happen. This is where I'm worried about buckling. Please make that bigger for me. And the algorithm will then redistribute the material such that the buckling load is improved 2.5 times in 5-10 minutes. We're not trying to say that if you don't have, if you have the computational resources, you should go for the full flush thing. Like if you do topology optimization for maximizing the buckling load explicitly, you will get a better performance. In this case, about 5 times over the baseline. The caveat is that that takes about 7.5 hours on a regular laptop without accounting for the significant tuning time that is associated with this type of formulation. Conceptually, this idea extends to 3D easily. Here we have a 3D version of the buckling column, where or buckling problem, where we've selected the bottom half of the domain, and the resulting structure with bigger length scales on the bottom doesn't look that different from outside, but if we take a slice through, we can see that we have the bigger feature sizes applied on the lower half. To get low compliance, the algorithm really wants to preserve the perimeter symmetry, and it does so by making the top members hollow. Over the past year or so, we've been interested in expanding this idea to more general design preferences. Really, preferences on how you interpret a design is not really limited to what's the fillet radius or what's the size of each member. And so what we would like to do is still have the computer do what it is good at, the exploratory part, but we would now like to have the user be able to have this two-pronged input where the user selects, okay, I would like to see something happen in this particular region, and then sketch or draw for us, okay, what is it that you would like to see? And then that should, of course, be taken forward as the computer iterates from that. When we start to talk about having something drawn or sketched and mapping that onto the topology, we need to talk about options that we have for image matching. And the first option would be to just impose a passive region. So say I draw an A, my A is king, you cannot change it, you can make a structure around it. And that was proposed last year within an evolutionary structural optimization framework where the input is a user drawing that is then mapped passively onto the topology or to the structure. The other option would be to encourage similarity through a constraint, and there's a number of papers that dive into that. I'm just showing one example here. These papers tend to use density-based topology optimization as their basis, and the input is usually not a drawing, but a patch of an image. And then this image patch is aggregated throughout the design space using a patch match algorithm. And then an additional constraint, an appearance constraint, is defined to make sure that the little image is represented within the topology. If we take a quick look at what these two things would mean in our context, we're going to be looking at a long cantilever beam and about 2/3 of the length. We're going to have a user draw a region where they would like to see a flower, and this is really where I'm showing that I'm an engineer, and the most creative thing I can think of to implement is putting a flower in a beam. And so if we impose this flower passively on the topology, we will see that the flower is replicated exactly as drawn. If we instead encourage similarity through a constraint, we will see the flower, but we will see that it's only replicated somewhat as drawn. One of the differences is, for example, that the way that the flower connects to the rest of the structure. And the fact that the algorithm has this flexibility to make slight changes it means that it can lower the compliance. Remember, we want C to be low, and so we can actually get a higher performing structural solution if we're okay with just seeing the intention more than seeing exactly what we've drawn. And so what we're going to be doing is we're going to use density-based topology optimization, provide an input that's a user-drawn pattern, and then use an additional constraint to make sure that what the user drew and the topology are matching. Because we're using the human to select where we want things to happen, it means that we can get rid of this patch match algorithm that some places are reported as being a bit heavy computationally. And we're still concerned about time. And so this is what we're going to be doing for the first 50 iterations. We're just going to do regular compliance-based topology optimization. At 50 iteration, when the design is somewhat formed, we will interrupt and ask the human to select a region where they would like things to change. And in this region, the appearance constraint is going to kick in. We've used the formulation by Neves and al., which is really just a squared distance between the image provided and the topology. And then there is this user set parameter, gamma, that defines, okay, how far are we allowed to veer. And so this is how it works. The computer does its thing for the first 50 iterations. The human goes in and says, yeah, I'm happy. In this case, I'd like to see sort of an X-brace pattern. We found that it works well to overlay it when selecting where they want it to happen, in this case up here. And now we see how the algorithm then takes that forward. We're going to see that there is some X thing going on in that region. It's not exactly as drawn by the human user. It's allowed to change a little bit shape, but we clearly see it appearing where the intention was. I will emphasize that the appearance constraint is slightly more computationally heavy to deal with than in the feature size versions of what we're doing. And so the runtime here is about 18 minutes from setup to convergence. The thing the user was worried about in this video was manufacturability or support material if printing the beam from below and up with 3D printing. And so we've done this little test experiment here where on top we have a beam where we've made no intervention, and then we made the intervention in the video before on the 3 bottom beams where we've specified that the appearance constraint has to be implemented more and more strictly as we go down the page. We printed samples of these beams with support material from down and up. And you can see visually that they are associated with quite different requirements of support material. We also measured it. We removed it and tested the beams experimentally, showing almost no difference between the numerical predictions and the experimental results. And perhaps more importantly, that the user intervention in this case had the ability to reduce up to 73% of the support material in a very short time, while only compromising the performance or the compliance about 3%. And so with that, I am at heart a structural engineer, and I believe quite firmly that we should really think about how do we design the structures of the future in a more carbon-friendly way. Part of the solution is getting algorithms to help us identify what do these new structures look like. And so the contributions that we're keen on making in our group is making it easy to identify how do we facilitate reuse, how do we facilitate using low carbon alternatives, and perhaps most importantly, how do we make it easy to reduce the material consumption within the construction sector broadly. In efforts to do so, we have to realize that time is a pretty valuable resource in this industry. And so we need to come up with new ways of designing where we also allow agency of the designer. An issue in construction is that the designer is actually the one signing off, this is safe, nothing is going to collapse, right? And that is difficult to do if you don't feel you own the design. And so we've developed this interactive structural optimization approach where we try to actively leverage the human experience, make the human an active part. And we've shown that this can improve buckling, energy absorption, eigenvalues, and as I showed last, things such as manufacturability. We hope that the impact that this type of work will have is that it will reduce the carbon associated with civil structures. You might think 25% concrete, that sounds like nothing. But if you scale that up globally, that corresponds to 2% of the annual carbon emissions today. And so there's really a significant potential that means that if you do a little, it actually goes a really long way. We hope also that we have the ability to change how engineers work with their computers instead of thinking that it's either me or the computer doing a design, thinking that it's more of a collaborative process. And finally, we're hoping that we can help contribute to a database of accepted high-performance designs that are out there operating that can feed into the future of generative AI methods. I would like to very much thank the people funding our work, without whom it would not be possible. our collaborators, both inside and outside MIT, but perhaps more importantly, the recent group alumni that are really the vehicles behind some of the work that I've shown here today. And with that, I thank you for waking up early on the last day of the conference, and I'd be more than happy to answer any questions that you may have.
That was a great talk. Thank you, very insightful. What I was curious was like the 3D printing optimization that you showed on one of the last slides. Have you considered any kind of boundary condition variations that could happen while printing, and like uncertainty?
So we have not considered that in this work. The premise that you can do topology optimization with uncertainty. It tends to become more computationally heavy to solve. And so the idea that we're chasing is that instead of explicitly including these types of mechanical considerations or uncertainty considerations, this is stuff that's ingrained in the human experience. So if you have an experienced engineer who looks at something and say, yeah, but I don't believe that the guy on the construction site will actually make this as perfect as this design requires, they will put in safety measures. Of course, the downside of relying on human experience is that if the human doesn't see it, it doesn't get included, right? But yeah, I hope that answers your question.
Yeah, you good?
Yeah. Yeah. Yeah.
The most challenging thing I found was communicating with these complex algorithms. Like you mentioned before, topology optimization is not very well suited for the sort of constraints that you see in real world problems. I'm curious what your thoughts are on like what sort of interaction modes or what sort of requirements do you want to see in these sort of topology optimization processes in the future? And maybe like I like that you were talking about like sort of drawing thing, but a lot of the like these mechanical constraints that you see from like which make sure that you fit to your building codes or whatever, those are actually giant discontinuous processes that you see.
Yeah.
Trying to apply these things is what kills using any of these
So thank you. It's interesting that you say that. So in our survey, we had expected to hear almost unanimously, the building code won't allow us to do this. Like it will never happen. But none of our respondents referred at any time to the building code. So I think the challenge comes before that. The challenge comes in getting familiar with the tools. To have that happen, the tools need to be easier to use and access. And we're hoping that by reducing the computational time, having you have sort of an input that guides you towards a solution that you're likely to accept, you can sort of also build up the experience level that way. So that, yeah, I know this work, now I can graduate to the buckling code or whatever, right? So I think there are many things to tackle in that. First is to realize that the challenge is there to begin with. And that is, I think, what I would like to see happen first. Yeah.
Hi, I really like the user study you had at the beginning, and I think we could all do with a little bit more of that in our field, in computer graphics. So maybe as sort of like a teaching opportunity for us, how do you go about, assembling a user study with highly skilled professionals, and how do you go about having like a diversity of ideas and opinions about the field represented in such a study?
Yeah, that was actually a challenge for us. We went through the professional organizations. We chose to limit the respondent pool to the northeastern US because if you go to California, the driver for structural engineering is going to be earthquakes. And so we did not want that sort of regional influence to make it difficult to make any conclusions whatsoever about how the study was conducted. So we went through the American Association of Civil Engineers, I don't remember what they stand for, Structural Engineering Association, and got them at their meetings to talk about it. And through that way, we managed to reach out to some companies that were smaller entities, which we would not have been able to get response from otherwise. We did see that we were not able to get the big players' employees to respond as well, and so we did like poke some contacts there and be like, can you send this around? Regretfully, I would have liked that we wouldn't have to do that, because that could, of course, spoil the pool a bit. You don't need, if your group is sort of specialized enough, having more than 30 responses is adequate to make statistical analysis on it. And I think we ended up at about 40, so it's not a huge pool, but it does say something about the major inhibitors at least.
Sorry. Maybe I can use the mic holding privilege. Thank you for a very interesting talk. So you made the case for weight reduction in building material as encouraging carbon usage reduction. And we are familiar with methods for weight reduction where the goal is weight reduction, like for prosthetics or aeronautics or applications like that. But you're specifically making the case for carbon reduction. But your formula that you presented for embodied carbon, or whatever it was called, seems to leave out several factors that encourage carbon reduction as well. I mean, you alluded to manufacturability a few times, but not explicitly in the context of how complex manufacturing processes or manufacturing processes that are not traditional increase carbon cost dramatically. You didn't talk about durability. If the structure lasts 100 years rather than 10 years, then the carbon reduction is again tenfold at least. And the last thing would be like mass manufacture, which can, again, like if you're making the same piece 5,000 times, you dramatically, again, save on the carbon usage. So I'm wondering if these complex structures that your automated systems produce give, with one hand, by reducing material carbon usage, but take away, on the other hand, by increasing the carbon usage of every other part of the system that actually produces them and the durability of and lifetime of the structure itself. So I'm wondering if these are things you've taken into account within automated workflows and not just the user coming in later and saying, hey, this is not going to tick off the boxes on these other carbon reduction strategies.
That's an excellent question. And some of the concerns that you're raising are already baked into this formula. So say if you do prefabricated concrete, typically the embodied carbon coefficient that you would take is lower than if you're doing on-site casting, because, as you say, the waste is more. The durability issue is not talked about a lot, but the fact is that when we when we take buildings down, most of the stuff is not ruined. We take down stuff way, way, way before it reaches its end of life as the construction practice is today, because we are designing things for 50 or 100 years, but then after 20 years decide, you know what, there should be a warehouse here instead of a bookstore. And so this is definitely a conversation that needs to be had. Another concern in this area is that when we're designing for 50 years, we are assuming that the loads that are happening today are going to be the same in 50 years. I dare say that that's not likely to be true with what's happening with the weather systems at the moment, right? And so that is another complicated conversation that we need to have. Should we start designing for shorter and then facilitating repair, and how would we do that? There was one, yeah, so one more thing in that is that we have been, some places in the world, the US and Europe specifically, the main driver of construction has been how do we make it easy to make, and that will always default to prismatic shapes. That does not need to be the case. Like if you start mass manufacturing things of more complex shapes, sure, maybe the upfront cost of making the more complex formwork that is reusable might be slightly higher, but that can pay itself back. So I completely agree with you about the concerns, but I do not think that they are necessarily showstoppers.
Thank you.
So you mentioned a bit at the end the generative modeling stuff, but if the chief concerns of people are like user time, compute time, and then also interactivity or ability to condition the output on these kind of heuristic or semantic characteristics, then presumably something people are looking into already is doing ML surrogate modeling.
Mm-hmm.
So replacing the whole end-to-end optimization with a sort of conditional inference. What stands in the way of that being a more prevalent approach here?
The availability of data, that there's not a realistic data set that you can train your models on.
So you can't use the current optimization methods as their own sort of data generation?
You can, but the only way that has been done this far is with very simplistic optimization results. There's not a database of this has actually been accepted, this is actually out functioning, and this is taken into consideration all of these complex, more realistic constraints. It's only very simplistic approaches that have been. You are not buying my response.
No, I'm just
maybe we
curious.
can talk more about that. But yeah, it's the availability of data that's the main bottleneck.
Thank you.
Hmm? Yeah, of course. Yeah.
I'm a software engineer who worked in structural engineering software for like 20 years already.
Yeah.
So I think I really appreciate your talk, and it's really interesting. But I think I just have one suggestion.
Yeah.
If you can somehow integrate code check with your optimization, that will actually be really a real thing. Because in my mind, because structural engineering world, strictly we are restricted by code.
Mm-hmm.
So everything has to go through code check, very strict review, and with your workflow plus code check, then it will be really good application that industry can use.
That's an excellent suggestion. I'll have someone do that next. Thank you.
Thank you again.
Thank you.